This is Alana Lynn doing Lab 7, the Black Hole Mass Lab Report. The purpose of this lab is to investigate gravitational force and use that to calculate the mass of the object exerting that force, in this case, a black hole. Through this model and the equation for gravitational force, I found the mass of the black hole to be 3.78 times 10 to the 31st power in kilograms. For this lab, I edited the code from Lab 6 to model the new star data and output the values. To do this, I had to change the star's mass and load the new star data. I kept the time step at 86,400 seconds, or 1 day, because it's small compared to the total time of nearly 4 Earth years. I used the position data given in the star data to calculate the x and y components of velocity. The while loop allows it to calculate the velocity over each change in position given in the data. IDX is simply a counter used throughout the code to keep track of how many lines of the table have been gone through. To find the force, we need to know the change in momentum, so I calculated P initial and P final, the momentum, for each step. The change in momentum over the change in time is equal to the net force. This will be used in the equation to calculate mass. I used the net force and the momentum principle to calculate the perpendicular and parallel components of the net force. This allows the model to show the curving motion of the star. The arrows of the model represent the different components of the net force and also the total net force itself. The black arrow is the net force, the blue arrow is the perpendicular component, and the red arrow is the parallel component. The what does it mean question asks how does these quantities relate to dp/dt and its components. These quantities are the same in magnitude and direction, but their meanings are a little different. The force quantities show the push and the pull on the mass in question, while the change in position over change in time quantities are showing the movement of the mass. They're connected because the movement changes due to the net force. Then, I updated the position of the star by having it use the next coordinates given in the star data file, and adding the last position to the tail of the star, the black line that follows it. To get the formula, I used the formula for the force of gravity and solved for the mass of the black hole, m2. This formula took the magnitude of the net force, multiplied it by the square of the magnitude of the vector distance between the star's final position and the given position of the black hole, and divided this entire quantity by the gravitational constant and the mass of the star. I programmed that formula into the VPython to calculate the mass of the black hole, and then I had the model print the mass of the black hole out at the end. What if we switched the black hole out with a new black hole with a different mass? Could we still do this and calculate the mass? The answer is no. Everything would be the same, so we would calculate the same mass. But this situation isn't even possible, because changing the mass of the black hole would change the gravitational force on the star and change its path. The only way for the star's motion to remain the same is for a new force to act in the opposite direction of the gravitational force exerted by the black hole. Since the question states that there are no other forces, the question asks about an impossible situation. Again, this is Alana Lynn doing the Black Hole Mass Lab Report. Thanks for watching.